All right. Guys, we've already talked about some polygons. We've talked about triangles. A polygon is a closed plane figure. What does it mean if it's a plane figure? Yeah. So, I don't know, can you guys see these little things I got up here? So right now I'm making a figure with four, you guys can't see very well. D. Okay, so here on this side we have some examples of polygons. And then over here we've got some not polygons. So no 3D, no open ones, no ones that crisscross over each other. That's not a thing. We can't have ones with little tails. This one is not a polygon because that side is not flat. Okay, so it's got to have all flat sides. Everybody happy with this? Okay. Okay, triangle is defined as a three-sided polygon, and a quadrilateral is a four-sided polygon. So those are special enough that they have their own little names. The rest of them are kind of named off of like a pattern. Comes from Greek. Like tri, this is 3, quad is 4, like pent is 5, hex is 6, hept is 7, oct is 8, and you might be thinking October is the 10th month. Anyone thinking that? December is the 12th month. Do you see that it's all messed up like in our calendar? What happened is that a long time ago, Julius and Augustus Caesar decided that they needed their own months and added July and August, and everything that was after July and August got bumped back too. And that's why they don't match. Think about it. Okay, everybody happy with that explanation? We can just blame it on the Greeks. Okay, 9 is nonagon, and so on. After 12, they didn't want to make... 11 to 11. I don't know. No one likes 11. Hi. Okay, what did you guys say this one was? Okay, yep. That's a nonagon. Is it a polygon? Yes. Yes. Okay. What about the second one? Not a polygon. Okay, this guy? Not a polygon. It's got a curved side. What about this bad boy? Heptagon. Yep. Yep. Okay. Easy. Easy enough. Okay. Okay, so each segment that forms a polygon is a side of the polygon. So if you weren't convinced that the sides have to be flat and like straight, the fact that the sides have to be segments should convince you. Segments are part of lines, and lines are straight. Okay, the common endpoint of two sides is a vertex of the polygon. A segment that connects any two non-consecutive vertices is a diagonal. So A and E are consecutive because they follow one after the other. So non-consecutive is like when we skip. Yeah, B to D, A to D, E to C. So any of those connections would be diagonals. Everybody happy with that? Okay. All the sides are congruent in an equilateral polygon. We know that. All the angles are congruent in an equiangular polygon. We know that too. A regular polygon is one that is both equilateral and equiangular. When we dealt with triangles, we had some theorems that said if a triangle was equilateral, we knew it was equiangular and vice versa. Do you guys remember that? That's not true of all polygons. That's only true of triangles, because you can't have a concave triangle. Okay, more on that in a second. A polygon is concave if any part of a diagonal contains points in the exterior of the polygon. So you can see that this diagonal connecting these non-consecutive vertices is contained outside, or not contained, inside the polygon. So that one is concave. If you're like, oh my gosh, all these words, I can't remember all this vocabulary. You guys know that like con is with, right? Like chili con queso, it's like chili with cheese, right? What else is with con? Okay, that's all I can think of right now. But it's like with, right? Con is with. And a cave is like hollowed out. So it's like with a cave. Right? With a cave? You should be more excited about that. Convex is there's like no dents in it. Okay? If no diagonal contains points in the exterior, then the polygon is convex. It's not really with a polygon, but they can use this with lenses. You know, anyone wear glasses or contacts? The concavity or the convexness of the lens is what corrects nearsightedness and farsightedness. It's an interesting little fact. Yeah, so if you have a regular polygon, it's always convex. So if you think about trying to draw a triangle where all of the sides are congruent and all of the angles are congruent, you cannot draw that figure without a dent, with a dent, right? It has to be convex, so it has to be regular. Everybody okay with that? But if I think about a pentagon, I'll do my best to draw this. You could kind of like have a dent in it and all the sides could be the same length. Okay, I know it's a little bad looking, but just because it has the same length sides doesn't mean all of the interior angles are the same. Is everybody okay with that? Huh? It might work that way. Let me get back to you and see if I can find a counterexample, but right now it might work that way. I'm having trouble coming up with a counterexample off the top of my head, but that doesn't mean that there isn't one. Okay, so for these we're going to tell whether the polygon is regular or irregular, and then we're going to say concave or convex. So let's just start with the first thing first. So we'll do this regular or irregular first, and then we'll do this. So go through and say, is it regular or irregular? And then we'll check those, and then we'll do concave or convex. Okay, this guy, regular or irregular? Irregular. Okay, the sides are all congruent, but these two angles are not congruent. All right, what about this one? Regular. What about this one? Irregular. Regular. Irregular. It's tempting to say it's regular because it's like 90, 90, 90, 90, but those are not the only interior angles. Like this angle right here, that's 270. Does everybody see that there's like a big obtuse angle right there? Okay. Well, it's not obtuse because it's more than 180, but there's a massive angle there. Okay. All right, let's do the second part. Tell whether it's concave or convex. Do we need time or can we just rattle them off? Concave or convex? Okay. Okay. With a hole, with a little dent, a cave. Good. Okay. You'll use this word concave again when you start talking, when you get into like, I don't know about algebra 2. I know for sure in pre-calc. You guys know when you started talking about parabolas and how they would open either up like a cup or down like a frown? When you get into pre-calc, you're going to call this concave up and concave down. And you'll have all of these fun tests for concavity. So you'll use that word again. All right. Polygon, exterior angles, sum, theorem. Oh my gosh, it's a lot of words, but it's really easy. Okay, so if you can imagine this collapsing, can you imagine it collapsing down to just a single point? Okay, if you can imagine this collapsing down to a single point, you can kind of see where this comes from. At a single point, if I spin around it, it's got to add up to 360 degrees, right? So if I collapse this down to a single dot, the sum of these angles has to be that entire full turn. That make sense to everybody? Okay. So that's it. It has to be a convex polygon. It doesn't work on those weird concave ones. That throws a wrench in everything. All right, so if we look at how the heck can we apply this, we can use this to solve problems. How many exterior angles do I have? 1, 2, 3, 4, 5. So all 5 of those have to add up to what? 360, so I can make a cute little equation. I can say that, we can even combine like terms here. I have 2x here, an x, and another x. That's 4x, right? And then I've got 88 plus 52. I've got 90 plus 50 is 140 plus 12. Thank you. Okay, and then we can solve for x. Is it B? Okay. Ta-da! So that ended up being a really easy problem if we can remember that all of those exterior angles, if I collapse that down to a single point, I can see that they have to add up to 360. Okay. All right, let's go back. Before we move on, let's look at something fun here. Can we go back up to this picture? We are going to use this on the next page, so this is not going to be a waste of your time, I promise. Would you please extend one of these with an auxiliary line? Oh, no, you don't even have to do that. Okay, sorry, scratch that. Let's just zoom in on this. Okay, so here is my exterior angle. Okay, and then on the inside, I'm going to have a corresponding interior angle. What do you notice about the relationship between those two angles? to 180 because they add up to a straight angle that makes a line, right? Everybody see it? So this, can we call this angle 7? The measure of angle 1 plus the measure of angle 7 is 180 degrees. Oh, my board is doing nothing. So they are supplementary. They are a linear pair. Oh. Oh my God. Oh. Okay, hold on, let me fix it. It's gonna keep doing it if I don't do this weird thing. You know how when your Chromebook is misbehaving and you reset it, you can like, it kind of does the same thing. Okay, so we can use this fact to solve problems. Everybody happy with that? Supplementary? Okay. All right, let's look at this. All right, let's draw. This is what I was thinking when I was like, let's draw auxiliary lines. Let's draw these auxiliary lines so that we can see the exterior angles. Okay, so I've got 1, 2, 3. Everybody see them? I could have drawn them going the other way, but after you pick a direction, it doesn't matter which, you just have to be consistent. Okay, and then kind of go around like a pinwheel. Okay, what does the sum of these 3 angles have to be? 360. Can we pretend like this is regular for a second? Okay, so regardless of whether it's regular or irregular, can we pretend like we know that it should have the same amount of degrees on the inside when we add up the interior angles? They'll just be distributed differently if it's irregular? Okay. All right, so if we pretend like they all have the same measure, what is the measure of one of our pretend matching exterior angles? Wouldn't it just be 360 divided by 3? Which would be 120. So we're going to pretend like each of these is 120, which if we now think about what would be supplementary to 120, 60 okay, is 180. Everybody okay with how we got that? So when we had 3 sides, the sum of the measures of the interior angles would be 180. And we already knew that because of the triangle sum theorem. But it's always fun to be able to get the same result in a different way. Okay, let's try this one. I'm going to let you guys do this one. I'm going to leapfrog and do this one with you. Okay, so we'll just go right here in the table. Maybe I'll go this way. I'll go backwards this time. So you can see it doesn't matter which direction you go as long as... Okay, so this time, how many exterior angles do we have? 5. So we're going to take that entire 360 degrees and divide by 5. So each exterior angle, if we're pretending it's regular, is 72, which means that the interior angle is 108. Okay, and then we have how many of them? 5. 5 times 108. Ooh, good. Okay, do you guys think that you can do the last 4 or 5?
Yeah.
Okay, go. So, if you've gotten this far, I want you to look at it very carefully and see if you can tell what's going on. Oh, beautiful. Okay, we're just adding 180 degrees. Oh my gosh, my brain is non-compliant today. Anyone else have a non-compliant brain that is reluctant to come back from break? Okay, so this, if you think about this as being like our x, and this as being our y, input, output, okay? We're going to use algebra for those of you who are like, I miss algebra. Well, it's back. Welcome. If I look at my change in y, it's 180, right? Right? Okay. Okay, and what's the change in the x? Yeah, it's just plus 1. So the run is just 1. Can you tell what the slope is? 180. Okay, so our m is 180. Now, here's the question for this is the one that'll separate the men from the boys. Can you work backwards and find the b value from the y-intercept? Does everybody understand what I'm asking you to do? Okay, do it. What'd you get? 0 what? 0 what? It's going to be negative, right? Negative 360? Okay.
But when the y is 0, it's 2.
Huh?
When the y is 0, the x is 2. And the x is 2, the y is 0.
Yeah.
What?
When the y is 0 degrees, the x is 2.
Yeah.
When the y is... Oh, yeah, okay. Yeah, I don't know why. Okay, I don't care about that one is why I was just not computing. Okay, so the b is negative 360. Okay, so can we write an equation for this in slope-intercept form? What would it be? Now, what if instead of an x we used n for the number of sides? Anybody have a problem with that? Okay, n minus 360. Do you guys remember factoring? You remember, do we have a common factor that we can factor out? 180, beautiful. I didn't write this very well. Y equals, what was it, 180 and minus 360. So we can factor out the 180. What's left? That's the rule. You take your number of sides, you subtract 2, you multiply by 180. Mic drop. Good job, guys. So, if you're one of those people like me who can't ever remember this, you can always find it this way by making yourself a cute little input-output table. Because I could never remember stuff like this. Okay, here we go. Is this our last one? Yep. Okay. Oh, I have one more I want to do with you because you've got ones like it in the practice and I want to make sure you can do it. All right, I want you to see if you can find the measure of angle E. So, how many sides are on this polygon? 6. So according to our table that we just made, what is the sum of the measures of their interior angles? Okay, so all of these cute little binomials have to add up to what? Okay, so that feels like an equation to me. If it were me, I would just be like, okay, x plus x plus x plus x. I would count out my x's and then combine my constants so I didn't have to deal with all of these. You know what I mean? You want me to show you how to be the... You see how this is a negative 8? Well, if I have a positive 2 and a positive 6, doesn't that cancel out a negative 8? So I'm like, okay, those are going to cancel. Look at the negative 4 and the negative 3. Don't they cancel out a positive 7? You see what I'm saying? Like, I mean, lazy, efficient, whatever. Two sides of the same coin. So really all I have are 1, 2, 3, 4, 5, 6, x. What did you guys tell me, 720?
Yes.
Uh-oh. What is it? What is it? Okay, so when we divide both sides by 6, we get 120, and then we want angle E, so we still have to add 6. Good catch. Sorry. Questions? Questions? Okay, off to the side somewhere where you have room. I want you to tell me, hold on, let me think of what I want to ask you. I'm going to give you the measure of an interior angle. This is example 5. So the interior angle is 140 degrees. Okay, find the number of sides for the polygon. You can either use the rule. I don't know that I would do that actually. I would use, could you use the interior angle to find the exterior angle? Okay, what would the exterior angle be? Okay, so then the exterior would be 40 degrees. Could I use the measure of the exterior angle to find out how many are there? what is the sum of the measures of all of the exterior angles every single time? 360. It's always 360. You see why it's easier to convert to exterior angles? So if I take the 360 degrees and divide by this 40 degrees, shouldn't that tell me how many there are? 9. So if I take my 360 degrees, okay, divide by my 40 degrees, then it should tell me that we have 9 exterior angles, which should also be the number of sides. Okay, now you should be able to do number 10. Okay? Because I didn't give you an example like that. Okay, questions for me? Yep.
With